Okay. So, you're allowed to keep that for notes. We're not turning that in. Okay? Here we go. But it's time to bring our attention back to the front. Okay, yeah, so let's bring our attention back to the front. Okay, so the very first thing over there, what'd you put? What is the symbol we use and what does it mean? A. And this is the starting value of accumulation. The starting value of our independent variable where we're going to start accumulating from. A. Okay, what's this? X. Watch it. There it is, X. This is the current value of the independent variable. The current value of the independent variable. X. Okay, then next we looked at, so this object here, double question mark. What are those? I gotta remember which slider it is. Yeah. Right, the large purple one. I think it's this one. Got it. Completed intervals. Completed intervals. That's what those are. Completed intervals. And then what is the value? How do we represent this value right here? Delta X. Delta X. What does it mean? Yeah, so it's the set length of an interval, and we call that a moment. This is what a moment is. It's the width of a moment, delta X. So this is how we're breaking up we're partitioning all X values into moments. So delta X, the value of delta X is the same as the width of a moment. Okay, what was next? Gold. I think that's this one. And what is that called? The current interval. The current interval. Okay, and then what did I say first? Blue? All right, what is blue? dx. So here's how you can know that, here's the difference between delta x and dx. Remember back in the day when we talked about parameters and variables. Delta x is like a parameter. It's just we fix it. It's a fixed value. Once we set it, then we run the show, and it doesn't change. dx, on the other hand, is a variable. It varies from what to what? 0 to delta x in every current interval. So, I'll show you. I'll have to make that bigger. Oh, I thought I had it up here. Where's it? Oh, it's up here. There it is. Okay, there it is. So it's going kind of fast, but it starts at, right now it's going to start at 0, and then it's going to increase up to what delta x is, which I think is 0.8. Or no, 1 point something. 1.2? 1.3, something like that. So it keeps starting over at 0. Every time it gets to a new current interval, it's going to start over at 0 and increase to delta x. And then, boom, next interval, 0. dx increases to delta x. So delta x is like a parameter, dx a variable, varying through each current interval. It keeps starting over, keeps cycling. Okay, the red one. Left of x. What is that? Left of x. No, it's an x value. It's not an interval. Yeah, so it's the value of x at the beginning or the left side of the current interval. It's the value of x at the beginning or the left side of the current interval. So again, any questions on the quiz? Yeah.
So how would you put into words what dx is? Just the value.
Oh, dx, right. So what is dx? Dx is
Just say it's the change.
the current change in x in the current interval. So it's the change in x in the current interval. Yeah, dx is the change in x within the current interval. Other questions? Okay. Oh, sorry.
The number of completed intervals. Could we represent that as j?
No, so j will take on. So j is a changing value. It takes on j equals 1, j equals 2, j equals 3, j equals 4. So j is not the number of completed intervals. We'll do that today. J takes on every. It is the interval number, and it takes on every one. So 1, 2, 3, 4.
It's just that whatever you have j equals whatever number that's where it starts at.
It starts at 1. It always starts at 1, and that represents the first interval. So here's j equals 1. Here's j equals 2. Here's j equals 3. Here's j equals 4. So j in the summation notation, it takes on every value from the starting value below the sum to the number of completed intervals. So it is the number of completed intervals, but just at one time at the end. But then it takes on every value 1, 2, 3, 4, 5, 6, 7, 8. Yeah.
If you made j2, would it skip the first interval?
Yes. If you said j equals 2 to whatever the final interval, then you wouldn't add in the accumulation from the first interval. Yeah. Exactly. Yes, sir.
Can this be made available on Blackboard?
Well, it's in the video. Do you want the program to mess with it? Yeah, it'll be in the video. It'll be on the video. Yeah, this is all being videoed. And then you got your sheet to look over. Okay. Yes, absolutely. But thank you. Okay, last chance. So, again, what is our journey? We know, and look, we haven't even started talking about the rate function yet, right? So we know how fast our quantity is changing at every moment. We want to be able to figure out how much we have at every moment. And we need all this just about the independent variable, right? So all this. And what is all this for? What is all this about the independent variable? It's all for what? Okay? It's about getting constant rates from the rate function so that we can build amounts. So it's all about getting these constant rates from the rate function from which we're going to build the accumulation function. See that? So all this stuff about the intervals, current interval, completed intervals, now I'm showing you what that's about. It's about getting constant rates a constant rate for each interval. And then with those constant rates, we'll build accumulation. So let's do it. Ready? Any questions? Okay, so you know how fast the quantity is changing every moment. You want to know how much of it you have. So here's looking at when the current value of x is 6.75. Right? So we want to know what the accumulation is at every single moment. Well, let's pick one. Let's just pick one moment and figure out what the accumulation is at that one moment. But then all the others will be just like it, right? So this is one example, 6.75. So how much do we have at x equals 6.75? Well, that's going to be our f of 6.75. And that's simply going to be, we're going to find that by this principle, m times the change in x. M times the change in x for every interval. Because we have a constant rate in every interval, so we're going to use our constant rate m times the amount of change, and we're going to add those up. This is basically it. So we have the change from the completed intervals. When x is 6.75, there's 3 completed intervals. And we have the change from those. M times change in x, first interval. M times change in x, second interval. M times change in x, third interval. And then we'll have the change from the current interval, which will be m times dx. A little bit shorter, right? It'll be less. But it's the same principle for all of them. M times the change in x. We're going to add them all up. Okay? So the question is, how do we get these rates? How do we get these rates? Okay? So we go to the first interval. What is the constant rate in the first interval? So this constant rate right here. How do we get this value of rate of change, which will be our constant rate for the whole interval? R of what? We don't know what that is. But how can we know what it is for sure, though? R of A, right? That's R of A. It's the rate that we find from the left side of that first completed interval, right? And that's R of A. So this constant rate is R of A. Rate right here is R of A because it's the rate at the right side of the current interval. Or not the current interval, sorry, the first completed interval, okay? So therefore, how are we going to get the rate for the second interval? Well, it's the rate that we get from this x value right here. Right? So this x value is going to give us a rate right like that. And so what x value is that? A plus delta x. That's this constant rate right here in the second interval. And it comes from the rate when the x value is this right here, which is A plus delta x. All right? What about the rate for the third interval? A plus 2 delta x, right? So this x value is A plus 2 delta x. That's the x value we want to plug into our rate and get this constant rate right here for that whole third interval. Okay? What about the current interval? A plus 3, okay? And we know that's the same as left. We'll come back to that later, okay? We're going to work on completed intervals for now. But that A plus 3 delta x, just as a preview, that's exactly the same as what we call left of x. Okay? And we'll go back to that later. So let's look at our completed intervals there. Looking at our completed intervals. What happens in those completed intervals? We keep doing the same thing over and over again. Rate, constant rate times change in x. Constant rate times change in x. So when we have 560 completed intervals, we don't want to write all those out. So what tool do we have? Since they're all the same, we can just write them once and then denote it as summation. Okay? So this is the idea of summation. They all look the same. So let's just write it once and then have some kind of notation that tells us what will happen as we go from one to the next. Okay? So this is it right here. So this is our summation of they're all rate times change in x. Okay, so let's see how this works. So here's the interval number, and that's j, right? So j represents which interval you're talking about. J is 1, and then j is 2, and then j is 3. 1, 2, and 3. Okay, so when j is 1, or let's look at 2. When j is 2, notice you have a plus how many delta x's? 1. And when j is 3, how many delta x's? 2. So how many delta x's are you adding in the j interval? J minus 1, right? There's always 1 less delta x than the interval number, j. So that x value then to get the rate for the jth interval is always a plus whatever your interval is less than 1 number of delta x's. Do you see the pattern? Okay, so that's what goes there. That's what goes there. And so when you see this part of our accumulation function, you have to see this as secondary. This is just a little detail. What is the thing? The deal here is that this is m times the change in x plus summation plus m times the change in x when j equals 2 plus m times the change in x when j equals 3. Plus, if this is higher, right? We have 3 completed intervals, but if this was higher, we would just keep adding m times the change in x, m times the change in x. This thing inside is just simply what? To get the x value for the jth interval. It's just getting the x value for the jth interval. That's all that is. So when you're looking at the whole function as a whole, blur your eyes to this. Don't let this distract you and overwhelm you because it looks ugly. This is just simply a rate times the change in x, and we're going to sum a bunch of those together. That's what we're doing. So, primary, like this, secondary, okay? Don't let that detail freak you out. Okay, let's go back. So we've got this. That's how we represent then the sum of accumulation and the completed intervals. All right, so what about the change from the current interval? Let's focus on that. And what do we say? So I've got that as red down here. Let's do it in red. So a plus 3 delta x is essentially the same thing as what? Or it is exactly the same thing as what we're calling left of x. And this gives us some insight into this function left of x. What is it? It's going to be a plus, how many completed intervals? It's 3. How many is that in this situation? All of them, right? How many completed intervals do we have? 3. So we're going to start with a, and we're going to add 3, or the total number of completed intervals of delta x to get to left x. So let's write that out. So what is left x? Left x is essentially a plus what? The number of completed intervals. Times delta x. That's what the function left x is. It's a plus the number of completed intervals times delta x. Takes you right there to that x value at the left side of the current interval. Another question?
I thought that delta x was supposed to be dx.
No, we're saying we need to get this x value. We need to get this x value. So what? So we're saying what x value is this right here? It's a. Gotta do this so it gets on the video. Okay. So it's going to be a plus 1, 2, 3 delta x gets us to left x. Why? Because left x is from here, it's this distance right here. That's left x. So it's a plus the number of delta x's, that is the number of our completed intervals. You see? It doesn't have anything to do with the current intervals. It's getting up to it, right? It's getting up to it. Okay, so the only thing that's left is figuring out the number of completed intervals. How many completed intervals are there? If you are the current value of x is x, and you have a, and then you have delta x. So given x, a, and delta x, how do we figure out the number of completed intervals? That's the last piece of the puzzle. Okay, so let's investigate that for a moment. And you should have read about that, right? Okay, so let's look at a similar situation here. So let's make a is 0.5. Let's make it 0.67. And let's make delta x a little smaller here, 0.62. Okay, so here's a scenario here. I've got a is 0.67. I've got delta x, our parameter set at interval width of 0.62. So we're not confused. Let's make a 0.87. A is 0.87, delta x is 0.62, and the current value of x is 9.21. How many completed intervals? How many completed intervals from here to here? The last piece of our puzzle. Now, for this example, you could sit there and count. You could go, it'll take you about 13 seconds, but you could do it, right? You could count these out. But we want a mathematical way, so suppose, we'll get to an example where delta x is very small. So suppose delta x is 0.13. You wouldn't be able to do that. We need a mathematical way to get the number of completed intervals between A and X. So here's our A, here's our X, and what each delta X is like this. So we're asking how many of these fit into that span from A to X. Okay, so what's the X minus A? What is that? Okay, so it's your distance of your interval from the starting value of x to the current value of x would be x minus a. And what are we asking about that? How many delta x's what? Fit into that. What operation is that? Division. We're asking how many delta x's would fit into that. All right, so let's do it. So it's x is 9.21 minus our 0.87 over 0.62. Okay, and oh look, I got a calculator right here. 9.21 minus 0.87 over 0.62, and we get 13.452. How many completed intervals are there? What's the 0.452? Tell me. Delta x?
dx.
Dx. The 0.452 is dx. So we have 13 intervals. Oh no, wait a sec. That's not right. This is a it's not dx because it's 0.452 of an interval. So 0.452 times delta x would be dx. So this is a fraction of an interval, 0.452. This is because it's a number of intervals. Make sense? Yeah, so we have 13 plus 45% of an interval. Yes, that's what we need. Right. So what we need then is we need just some mathematical operation that takes this and just removes this extra amount. So we get this just the whole number, and that's called the floor function. So if you do, and then you symbolize it this way. So if you do the floor of 9.21 minus 0.87 over 0.62, and then so you do that quotient, and then take the floor of it. Well, let's do it. So in graphing calculator, what you're going to do is you just type floor, and it appears. And so then I'm going to go 9.21 minus 0.87, and then divided by, what am I dividing by? 0.62. And it takes the floor. The floor of that is the number 13. Floor is the operation that just removes whatever extra you have from the last whole number. It just takes it away and gives you the greatest whole number less than whatever value you put into the floor. And that's what we want, to get the number of completed intervals. Therefore, the number of completed intervals is, but in general, what is it? It's x minus a over delta x. Gets us how many intervals including the fraction of the last one, the current interval? We don't want that current interval. Floor it. And that gets it. So now we have all the pieces. We have all the pieces of the accumulation function. So let's put it all together. Ready? Here we go. Any questions on figuring out on how we got the number of completed intervals? We got the whole span from A to X. And we want to know how many delta X's fit into that. That's division. But that will also give us the current interval, the percent of the current interval that we're into. We don't want that because we just want a whole number of intervals. So we apply the floor to that. So there's our formula for the number of completed intervals, x minus a delta x, over delta x, the floor of. Okay, so let's go back to my PowerPoint here. Where is it? So we said that left of x, this is essentially plus r of left x. And then how can we write dx in terms of x? So how can we write dx, this little change, in terms of our input variable x? X minus left x. Let's try it again. Plus r of left x times x minus left x gives us dx. Okay? And so in general then, if we have lots of completed intervals, then what's going to go right here? That is, what's that number right there? That's the total number of completed intervals. What is it? We just found it. The floor of x minus, you're getting so smart, you know that? The floor of x minus a over delta x goes right there, because it's the number of completed intervals. J will start at 1, and we'll count up to the number of completed intervals, whether that's 50 or 1,000 or 1,000,000. And then we know that the last thing is that this left x function is what? Left x is left of x. We know it was a plus how many intervals of delta x? The number of completed intervals. So we're going to use it again, right here. There's the left x function. Here it was a plus 3x, but 3 was just the number of completed intervals. There it is, a plus the number of completed intervals to get to left x. So now we know what it all means, okay? But when you look at that, you have to, the very overarching thought that you have to have is what? M times a change in x, plus 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 m times a smaller change in x. And that's it. That's it. That's your overarching thought when you see this. You don't get scared by these symbols, all these different symbols. We know what the details mean, but we keep the overarching idea in mind. Anybody have a question? All right. Why don't you talk about what was the big idea today, and then we'll have Top Hat. Go. Oh, yes. Yes. Did you put it up on the blackboard?
I still
Okay.
have the room numbers,
Okay.
which is they said it's
Also
more
good.
than 24 hours.
Sure.
But I do have, like, I'm just going to tell them, here's the times for the review sessions next
Sure.
week, and then about the sign-up sheet for me, for my one-on-one.
And then you can tell them it'll be all on announcements. You could do that before Top Hat.
Yeah, okay, perfect.